the session today, Christina Brech, speaking on isometries of combinatorial spaces. Thanks.
Okay. Thank you, Kevin, and thank you to the organizers for the opportunity to speak here. It's not exactly, I hope you enjoyed the talk, but it's maybe a bit not on the exact topic. Most of what I will talk about is about the joint work with Claribet Pinha, but also with Valentin Ferenczi and Adit Kachuk. So the motivation was this theorem, which I guess is folklore, that every linear isometry of C0 and also of the LPs for P different than 2 are a sign permutation of the canonical basis. So you have a bijection of the natural numbers and a sequence of signs. Signs are just scalars with absolute value 1, and such that the basis is taken by T to this signed permutation. And also, I like to put as a motivation some sort of topological counterpart, right, which is the Banach theorem, where it says that if you have two compact Hausdorff spaces and a linear isometry between C of K and C of L, then it is induced by a homeomorphism between K and L. Whenever I say in this talk isometry, I mean linear bijective isometry. Okay, so just to be clear, but I won't repeat it all the time. And so indeed, Kevin, when we visited Virginia in, I think it was 2018 maybe, posed this question: what are the isometries of the Schreier spaces? So the Schreier families and the Schreier spaces are defined as follows. So the first Schreier family, the classical one, which was introduced by Schreier in the 30s, is just the families of finite subsets. So this means finite subsets of the natural numbers, which has less elements than its minimum. Okay, so and this condition is just some technicality. But important to understand the family is that, so you have finite sets as large as you want in the family, but the larger you want it, the further it has to start, right? The minimum has to be also large. And then you can take the completion of C00, so you take just the vector space of finitely supported sequences of real or complex numbers with respect to this norm. So you are allowed to take sums of absolute values of the coordinates as far as they are supported in some set of the family, of the Schreier family in this case. So this is a norm. And you can take, you can take the completion of this space, and then you get a Banach space. There are also sort of more complex versions of the Schreier family, which are the Schreier families of higher orders. So if you take a countable ordinal, you can sort of make some interpolation here. So you take elements of the previous family and you take finite unions of them. And these finite unions are restricted to some condition related to the first Schreier family. And so this is how you define the Schreier families for successor ordinals. And then for limit ordinals, you sort of take tails of Schreier families of some sequence converging to the limit ordinal, and you take the union of them. I mean, you have to take, I will mention why you have to take tails of these families, and just to point out that the increasing sequence converging to alpha might change. So for S alpha is not really one family. I mean, you can have several definitions for some S alpha, some Schreier family of some limit ordinal. Oh, here should be, yeah, the other S. anyway, and similarly, we can take again the same, exactly the same norm, and the completion of the C00 with this norm, and you get a Banach space. So what are the important properties of these families which allow us to consider these Banach spaces and which give some interesting properties of the Banach space? So one condition is that these families contain singletons. This is not really needed. You could, this is helpful to guarantee that the norm previously defined is really a norm, but you could just take the supremum, considering also the maximum of the coordinates, and then you would, so this condition we could get rid of it, but I will just put it because it is useful, and the singletons will play some role later. So if you don't have it, you can just add them. It is hereditary. This is also a condition that it's not really needed because you can always close under subsets. So when I say that these families are hereditary, I mean that if I have one element here, and then I take a subset of it, and then it is still in the family. But as I said, if I have a family with the other properties that I will impose, I can just take the closure under subsets and I get a hereditary family. So these two conditions, they will appear, but I mean, it's just because without loss of generality, I can assume I have these two properties and they are helpful. I mean, they make arguments easier to write. And then as alpha is also compact family, so we look at this family as a subset of the contour set. We just associate, so if I have some element of S alpha, I just associate it to its characteristic function here. So I can see this as a subset of the contour set, and then I just, the family is compact if it is compact as with this topology, with the inherited topology from the contour space. And finally, these families, these Schreier families, they are all spreading. So spreading is a condition which says that the family is closed under pushing elements to the right. So if I have one element of the family and I take larger integers corresponding to each of them, then I still get an element of the family. So the Schreier families have all these properties, and these properties guarantee that the canonical basis of the C00 is indeed a one unconditional Schauder basis of the corresponding Schreier spaces, and which is also shrinking. So as I said, the most important here is that the family is compact to guarantee that this Schauder basis is shrinking. This will be what I will mostly use. Okay. So what are the combinatorial Banach spaces? So these are just a generalization of the Schreier spaces. So now I take an index set I, which doesn't have to be the natural numbers, but for the separable context, it is the natural numbers. And then I take a family of finite subsets of I. So all the elements of F are finite. And then I say that it has the corresponding properties that I just checked that the Schreier families have if they satisfy the condition that we just mentioned. So it is hereditary if it is closed under subsets. It is compact if I again associate to each element of the family F, I can associate its characteristic function. And then I look to F as a subset of this space 2 to the I, and it is compact if it is closed as a subset of 2 to the I. And spreading is a condition which makes good sense whenever I have whenever I'm working in the natural numbers. For instance, if I is some larger ordinal, we could also, so if we have some order in I, right? In particular, if you have an ordinal or a cardinal, it makes sense. I mean, it is formally possible to define what a spreading family is, but it is not very helpful, in particular if you are working with larger infinite ordinals or cardinals. Spreading and compact properties are incompatible. So if you have a spreading family, it won't be compact. And so since I need compactness for what I will do, I will restrict the notion of spreading to the context of the natural numbers. And just to put it shortly, a regular family is a family which is hereditary, compact, and spreading. And in general, I'm also assuming that all the singletons belong to the family. I just could add them, and it keeps all these properties. So having a family with these properties, I can define now a norm on the C00 of I. So I have now larger sequences indexed on a larger set I. And so if I take a finitely supported sequence in C00 of I, then I define the norm similarly, allowing sums of absolute values for whenever they are indexed in some elements of the family. And because the family has all these properties, again, this is, okay, then I take the completion of this norm space, I get a Banach space, and this is, it will have, again, the E, now the EIs. So let me put here EI. This will be a Schauder basis, a long Schauder basis, which has similar properties as previously. So it will be, whenever I have a cardinal, maybe it's better to write it in a cardinal so that I have an order here. But if I have something like this, then this will be a one unconditional Schauder basis for this Banach space, and it will be also shrinking. Okay, the motivation for, well, my motivation for Kevin's question is that C0 can be seen as a combinatorial space, right? If we just take the family of the singletons, this family satisfies all these properties. And if you take the supremum allowing only sums over singletons, you just get the supremum norm. And so combinatorial Banach spaces are a natural generalization of C0 of C0. And also of C0 of some kappa or some gamma for some larger index set gamma. So we wanted to know what are the isometries of these spaces. So the main results, I put here several versions. I will comment on each of them, but is that if you have an isometry between two combinatorial Banach spaces, then you have a bijection of the index set, right? So you have F and G families with the same underlying index set. So there is a bijection of this index set and a family of signs, so that T is always a sign permutation of the basis. And so for hereditary and compact families F and G with some additional properties. So let me mention what are the versions. Oh yes, so and moreover, this permutation will take one family onto the other. Okay, so this is, I will use it later. So the first version by Antunes, Binland, and Shu was that if you have a Schreier family of finite order, both on the domain and counter domain, so whenever you have an isometry of one of the Schreier spaces for finite order, then you can get this permutation. And indeed, I will also mention later, but this permutation in that case is just the identity map. Later, together with Ferenczi and Kachuk, we got the same result, but now for F and G not necessarily being the same. but they are regular families on N. So we have, so in particular, when I say regular here, the important additional property is that it has, it is spreading, right? So, and this is the version together with them. And then later with Claribet-Pinha, we proved the same, but we generalized in particular for uncountable index sets. So, and then we had exactly the problem, by which property do we have to replace the spreading property, right? Because on N, we assumed spreading, and that was useful in the proof. So we had to find out what was the condition to replace. And the condition is this one, that the singletons of I, they are in the closure of the maximal elements of the family. So when I say maximal, I mean maximal with respect to the inclusion. And so the singletons, they are in the closure of the maximal elements of the family. And this is true for regular families, for spreading families, because whenever you have some singleton N here, and then if it is not maximal, I mean, you can extend it to some maximal element, and usually you can assume that it is the minimum. So you will extend it to some maximal elements so that it is the minimum. And then you can push these other elements in this direction and get a disjoint set here such that this is still the minimum, for instance. And then push it again, so you get a sequence here of maximal elements, and if needed, you can also enlarge this set to get it to be maximal. But you can, so by pushing using spreading, you get a sequence of sets such that the intersection of two of them is only this N. So exactly you have this singleton being in the closure of these maximal elements. Okay, and so this is how we figured out what was the needed condition to prove in the uncountable context. So just to mention some non-separable examples, right? Because I gave as a motivation the Schreier families on N. So for larger sets, we have some interesting constructions of spaces coming from this family, so combinatorial spaces or combinatorial norms, which give interesting properties. So let me first mention this result by Lopez Abad and Todorcevic, which says that if a coloring from finite subsets of some cardinal, infinite cardinal kappa in two colors, it witnesses that kappa is not an omega Erdős cardinal. I mean, the definition is almost what is written here, but I won't give the definition, but this is some combinatorial definition for a cardinal. So again, a coloring witnesses that this cardinal is not omega Erdős if and only if this family, oh, here it's not really correct. Okay. If a family coming from the coloring, so here instead of all the finite subsets, I should say that all the finite subsets, all the subsets of F with the same size have the same color. So it's not for all of them, but just when you have a fixed, any fixed size here. So this family is hereditary, compact, and large means exactly that you have finite sets, but of arbitrarily large size. So this is an equivalent condition, and they also prove that this is equivalent to having a Banach space with a one unconditional basis, which has no subsymmetric sequences. And okay, so this is just one family which appears, and it has all the properties we want. And also in a joint work with them, we considered, for example, I mean, in this paper, we constructed some version of some non-separable version of the Tyrosine space, and we used this sort of families in there. of course, our space that is much more complicated than just the combinatorial space of one family. We make some interpolation of families there. But just to give you an idea, if we have a family with these properties living on some cardinal kappa, and indeed you can assume it lives in the ordinal, which is the successor of kappa, then you can push this further and get a family with the same properties, but on a larger cardinal. So you will get from a family on a cardinal kappa, we get a family on the cardinal 2 to the kappa by using the complete binary tree and pushing. So just to so here I have the kappa, and so I have my family living here, and I push it here by just taking elements which are in the branches such that the images belong to the family here. So this is how I push a family from some kappa to the 2 to the kappa and get families, interesting families in larger and larger cardinals. So this slide is just to mention that the non-separable case has also interesting examples. So what are the ingredients for those theorems? So what we do is just, oh, I thought maybe I have, oh, I corrected, but I don't have the corrected version here. I'm sorry, anyway. So we look at if we fix an isometry between these combinatorial spaces, we look at the adjoint operator, and this is also an isometry. So, and there is this characterization of the extreme points of the dual bow of combinatorial spaces by Gowers, which says that the extreme points of the dual bow, and here is what I corrected, but I have again the wrong version. Here is just the sums, the index, sign sums of things like this. So I take here possible signs, and I take since my basis is shrinking, now I have this basis in the dual, and then I take these elements, and whenever I have such a sum which is indexed by a maximal element, this is an extreme point of the dual bow, and these are all the extreme points. And so isometries taking extreme points to extreme points, this already gives you that such sums have to go onto the same kind of sums on the other side, right? And then you have to work in order to get from a finite sum to get rid of it and just get what is the image of a singleton, right? Like of one element of the basis. And this is done in our first version, is done just by hand, sort of. We work by hand, so to get from these sums into, so the image, right, of this element to get what are the images of this element. And then with Claribet, we managed to state it, to write it in a more elegant way, I guess, which uses the fact that these singletons are in the closure of maximal elements of the family. So you can approximate these elements of the basis by extreme points. And then in the weakly star topology, and then sort of use the isometry to write this one. Okay, and just a comment, in here I will put a question, and it might have a stupid answer, but I don't really know, so maybe someone in the audience can help me. So in the previous version, we can start directly with an isometry on the dual spaces. Okay, while with Claribet, we needed this isometry to be weakly star continuous. So this is why we finally started with an isometry between the combinatorial spaces and then worked with the adjoint operator. But we don't know if this is just the same, right? If every isometry from the dual of a combinatorial space to the dual of a combinatorial space is always weakly star continuous, or something like that. So if someone would know, please let me know at the end. And then a further analysis of these objects. As I said, I mentioned when I stated the main result in these various versions that for the Antunes, Binland, and Shu version, where they have the Schreier family to, sorry, the family to be one of the Schreier families of finite order, they showed that the permutation is the identity, right? So, and in our version with Ferenczi and Kachuk, we also get that the permutation is the identity whenever I have any Schreier family of any order. So what about regular families, right? So can this permutation, what can we say about the permutation? Because we know that the isometry comes from a permutation, but now what are the allowed permutations, say? And also, what about the non-separable case? Then we proved that in the general case, if we have a bijection between, here I stated with the cardinal, but could be an index set, which takes one family, one of those families onto the other, it will be the identity map as far as I know that the Cantor-Bendixson rank of the singletons in these families is increasing, which for some similar reason that I mentioned when I said that you can push sets to the right and construct a sequence here, such that the singleton will be in the closure of these, will be the limit indeed of these sets. So for some similar reason for spreading families, the Cantor-Bendixson ring index of the singletons is not, it's not necessarily increasing, but it's already non-decreasing. So this is, and for the Schreier families, they are increasing. So, and this can be done even in the non-separable context, right? So the condition is that the singletons have to have Cantor-Bendixson rank increasing in both families, then it has to send, P has to be the identity map. Actually, so this comes, I mean, we managed to realize this because indeed, whenever I have this bijection P here, I have an induced homeomorphism between 2 to the kappa and 2 to the kappa, or 2 to the I or 2 to the R, or between the Cantor set and the Cantor set. And this homeomorphism is taking one family onto the other. So it is a homeomorphism of the families themselves. And then, so we extracted the topological information about the families. And finally, I mean, this is more combinatorial result of the same work, but we managed to prove that if a family is taken by a permutation onto another family, whenever it is spreading, so this is because we wanted to know what spreading families, what can we say about spreading families, because this is a rather strong condition in this context. And then indeed, the permutation might not be the identity map, but the family has to be the same. So this means that you cannot have two different combinatorial spaces coming from spreading families which are isometric, right? I mean, the family has to be exactly the same. And we were hoping with this that, so spreading families would give us representatives of isometric classes of combinatorial Banach spaces in the countable setting, but it is not true. I mean, there are compact hereditary families on N which cannot be permuted into a regular one, so into a spreading one. And then, so the regular ones don't give representatives of all possible combinatorial spaces in in the countable context. And just to mention two questions, so we could do, instead of putting just sums of absolute values, we can put sums of absolute values with p-norms over there. And so do similar results hold for these norms? And also, what about the non-surjective linear isometries between these spaces? I mean, because of course, this is a very rigid structure which we considered, right? So what can be said if we take something weaker? And okay, here are all the references, and this is all. So thank you very much.
Well, thank you, Christina. I have some comments or a couple questions, but if anybody else has a question, mine are more comments. Anybody? I don't hear anybody. Well, thank you for the nice talk. I appreciated hearing the overview. And so something I was thinking about a while back, and I meant to ask you about maybe some further research type of thing, is that there are some papers where they're looking at the characterizing the isometries between the spheres. And so, for example, there's something called Tingley's extension problem or something like this, which is if you have isometries between the spheres of Banach spaces, can they always be, are they always the restriction of isometries between the spaces? And so for a few spaces like James space and Cyrilson space, they've looked at, there are some papers on which they characterize the isometries on the spheres of these spaces, and essentially show that the isometries on the spheres have the exact same structure as the characterization of the isometries on the spaces, but the techniques are quite different because you're not looking at it's only on the sphere, so it's the linear structure sort of goes away. It's just onto isometries on the sphere. So it might be interesting to look at that in combinatorial spaces as well, because it seems to me that the techniques don't quite work the same way. And there's also the possibility that you could say something interesting. I mean, I think that there's some general questions about these, whether you can extend these isometries on the spheres to the whole spaces, and and it might be with different combinatorial spaces that you could say something in that kind of area. But that was just some thoughts I was having about that.
Yeah, I mean, you can think of these families also from just a topological point of view, right? I mean, when you don't look so much into the order, and then, I mean, that's why I put the Banach-Stone theorem at the beginning, right? Because you can also, so if you can also think, so if C of one of these families and is isometric to C of the other one, then they are homeomorphic. But in both cases, the linearity, I mean, shows up, right, in the proofs. I mean, in the classical Banach-Stone theorem, and here also the fact we are using strongly the fact that the extreme points are taken to extreme points, and this, of course, uses linearity, right? So yes, but I mean, it's. I also think there must be, because these are rather well-behaved families. I mean, from my point of view, I think most people look at them as maybe something strange, but for me, they are very rigid. So yeah, thank you.
Christina, I have a question. So you said you can prove, I forgot now exactly what it was. You can prove something for finite Schreier order, Schreier spaces, but not for...
No, I mean, the same results hold. It's just that...
no, okay, so sorry, it's omega 1. Oh, okay, so no, I misread. I thought omega, because there's a lot of...
no, the first version was for finite orders, right? With Kevin and
Thomas, we were proving we didn't think to go to the dual, and we proved it on the space, and things got really out of hand at omega, and And
Because,
when you go to the dual, things get a much a good bit simpler. I don't want to say it's simple, but it was definitely a bit easier.
so no, I'm asking this because I don't know. Do you know this paper by Gasparis and Leong in 2000? They found continue many complemented spatial subspaces of Schreier space, but only in the finite, only in the for finite order. And
they found continuum many, what, say again?
a continuum many complemented spatial subspaces. Complemented spatial subspace means generated by subsequence of the bases. But they can only do this. I actually looked at that and I tried to generalize it, but I couldn't either. They only could do it for Schreier spaces of finite order, not of infinite order. And because it also has to do with about the ideals of operators. So I wonder whether there's a similar reason why in your case it's more difficult, or so I wonder about.
Well, probably if you go with the basis, it is more difficult for a similar reason, but they were smart enough to go to the dual and work with
I see.
the extreme points on this. So they sort of, because of the problem they were trying to solve, were able to go to the dual and deal with because the problem is you don't know the extreme points on the space. Characterizing the extreme points on the Schreier space is, as far as I can tell, very hard.
Okay, so this was actually, oh yeah, I see. This is also in your paper with Thomas and Niels. You had this restriction, right?
Yeah, right. That's why we had that restriction. Yeah.
So from what I know, speaking about the number of ideals on Schreier spaces, I don't know yet whether this can be generalized for infinite order. So Kevin, you don't know whether your result.
No, we absolutely used it.
Yeah, no, I think I know. I thought about this too, and there is a problem, right?
Yeah. In fact, I thought about this problem that you mentioned, and didn't think about it very much. And then months later, you mentioned that you thought about it, and try to overcome this omega barrier, if you will. And I hadn't realized it was going to be that hard.
No, it looks doable, right? But then yes, I see. Yeah.
There is a recent paper by Piotr Borodulin-Najeja and Barnabas Farkas, where they also look to ideals of these of operators of these spaces, of the Schreier spaces.
Because okay,
but
so
I don't know.
Yeah.
So I on the archive?
Yeah.
Okay.
I think it's published.
Oh, okay.
But it's also on the archive, yes.
Yeah. Okay, so there's it only reminded me when you had this distinction also. So I was wondering whether there's some.
Yeah, here there is no distinction on the result. There is just a distinction on the difficulty because of the technique was different.
Okay. I wanted to make
a question.
Go ahead.
Hi, Christina. Hi, Kevin.
Hey.
So sorry if this was mentioned. Do you remember if there is anything known about the situation for that you asked about non-surjective isometries for certain simple Schreier spaces or things like that? Because in that case, you cannot work so easily with extreme.
I don't know anything about the non-surjective.
Okay.
So yeah, this is.
You know, that an interesting thing is that for Cyrilson space, I think the proof is easier than for Schreier space. The classification of the isometries.
But do you get something for non-subjective in this case?
I actually think you might. Yeah.
Yeah, I agree with that. Cyrilson for these things is easier than. Yeah.
It's easier, yeah.
Because
the norm tells you it tells you how to, do estimates on blocks, right? Because you assume essentially that the image of the EI is a block, and then you can do estimates on the blocks. And
and the other, I think the other reason is that Schreiers are hereditarily C0 when you take enough when you take enough blocks, then,
Mm-hmm.
well, in Zilsen, you can always
Mhm.
know you never get to little one.
Mm-hmm. Mm-hmm.
Yeah, I was actually, when preparing the talk, I was thinking about because there is this version with Jordian's table, right? Which is the version of the Sirius for the non-separable. And also I never looked at it, but it's probably also easier, though the construction is involving, but.
Mm-hmm. Okay, I'm gonna stop recording.